So what is probability in mathematics? Now, let us apply some context to it so we can see if we can, draw an association. If I say to you, are you going to the cafeteria? And you say, probably. What are you saying? You are saying yes or no. But if you're saying yes or no, say yes or no. All right, thank you, Miss Danica. So it says, if I say probably, I'm saying that there is a chance that I may go or I may not go because probably suggests some amount of, you are unsure. So probably, we use the word probably. I am saying to you that there is a chance that it may happen or there is a chance that it may not happen. Whatever the case is, you can't then say that I told you that I was going to do it. Because, say for instance, use the same scenario. Are you going to the cafeteria? And I say, probably. If I go, you cannot then say, so how you go to the cafeteria? Or you say you never did go to the cafeteria, right? I never did say that. What I said is probably, which means that there's a chance that I may go or there's a chance that I may not go. So if I end up going, that's the chance that I took and go to the cafeteria. So that is what probability has to be. It deals with the chance of something occurring, right? So just as though there is a chance that something may occur, there is also a chance that it may not occur, right? So what is the probability of an event? The probability of an event, let's say the event is A, let's just call it event A for now. The probability of event, well, let's write it in words. Um, so probability that an event will occur, it is the number of outcomes of A, which is event A, divided by the total number of outcomes, or sometimes referred to as the total sample space. All right. So that is what it has to deal with. So, so just as we mentioned a while ago, we talk about sample space. Can anybody give me what they think in terms of a definition for sample space? All right. So your sample space, because in the interest of time, would represent the total possible outcome of an experiment. So your sample space will, will be the total possible outcome of a particular experiment, whatever that experiment is. Your experiment could be flipping a die, flipping a coin. Well, roll a die, flip a coin. Yes? So when we talk about your sample space, so what we're going to do now, we're going to look at a few sample spaces. What we mean by uh, sample space. Let's use a different color to highlight these. If you just have one coin and you're going to represent the sample space of that one coin, it's just going to be head or tails. So there are only two possible outcomes. So there's a 50-50 chance, right? If you have two coins, then the sample space becomes a little different. All right. So here I'm going to use a table to represent this sample space. Let's say in this cut, we have coin one, and down here we have coin two, right? So on coin one, we have a head and a tail, and coin two, we have a head and tail as well. So is it likely to happen? And we can do the experiment right now. Anybody have coins? Yes? So, oh yeah. So if we go ahead, here I have two coins and you have indicated that they have as well. Now, if you should take your two coins and flip them, right? So we take our two coins and we flip them. So as it is now, I have just gotten one coin to land head and one to land tail. So that is a realistic outcome flipping the two coins. If I go again and flip the two coins, now I have both coins um, turning or facing heads up or showing a head. That is a realistic outcome of flipping the two coins. All right. So and if we continue, we can see other outcomes. What are the other possible outcomes? As we just realized, it is possible to get two heads. It is possible, as we figured saw from the experiment, it's possible to get a head and a tail. It's possible to get a tail and a head, and it is possible to get two tails. So the total sample space would be what is represented here in this red color. So the sample space for flipping two coins would be head, head and a tail and a head, and a tail and a tail, right? So this would be the sample space. I mean, not necessary to have the brackets, but we could have easily even keep do this to make sure we have them separate, but normally it's just left it as a table, and you can just read the information from the table. Because I could ask you what is the probability of getting two heads, right? Or a head and a head, right? We could we could very well have had three coins. So what would be the sample space of flipping three coins? Well, we know what it would be if we have two coins. So all we're going to do is just build on that information, right? So if we have two coins here, we know what is the outcome of flipping two coins. Those outcomes are a head and a head, a head and a tail and a head, and a tail and a tail. And if we just have one coin, the outcome must be heads or tails. So the reality of it is, if we have three coins and flip them, is it true that we can have heads on all three coins? All right, so that is possible. So we can get a head, and another head on all three coins. Is it possible that when I flip, I can get two heads and a tail? Is it possible that I can get a head, a tail, and another head? Is it possible that I can get one head and two tails? Right? So when we say the tail, just making reference to the alternate side of the coin that does not have the face. Heads just meaning that portion of the coin that represents a face. All right? We could have a tail, a head, and a head. We could have a tail, head, tails. We could have a tail, heads, and we could have a tail, right? Which would be the alternate side to the heads. So these are possible outcomes. And notice I represent the outcomes in red so they can easily pick up on we expect the outcome to occur. So I could easily well go and ask you, what is the likely chance of getting two tails? No, so you have to look at all the outcomes that have two tails, right? What is the likelihood of getting one head? You have to look at all the outcomes that have one head, right? So those are things that a question can ask, and we're going to look a little bit later on how would we go ahead and represent it. Say for instance we have one die, right? What are the outcomes on a die? One, right? So those are the outcomes, which in other words is the sample space. Okay. Say for instance, we had one die and a coin. Let's use a table to represent the sample space as well. So we could have the die, and then here we have the coin. So on the die, we expect to have 2, 3, 4, 5, 6, and on the coin, we expect to have the heads and the tails. Is it possible to flip the coin and get a head and roll the die and get a 1? Is that a possible outcome? So it is possible to get a heads and a 1. It's possible to get a heads and a 2, and we can see all the possible outcomes here. Tail and a 1, tail and a 2, tail and a 3, tail and a 4, tail and a 5, tail and a 6. Right? So all of those are possible outcomes that you can get if you have one die and a coin. So you must know how to derive the sample space. And then from your sample space, answer any questions that they give you based on that sample space. There's one more options that we're going to look at is, what if we had two dice, right? The two die are two dice. Two are dice. All right, this table is a little bit more complex. Well, because there's way more information that in this table. All right, we would have played a number of games that involves using dice, right? Is it possible that when you roll the dice, you can end up with a 1 on both dice? Is it possible to end up with a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6? All of these are possible outcomes. Agree with it? Not sure? Let me know. We agree we can get this on the dice? We can get a 2 and a 1, can get a 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. And it goes on. That's right. Yes. Because you are first used to this. All right. So that is what we would end up with for the outcome. What we're going to look at now is how to solve a few questions that involve probability. All right, so we're going to look at these examples for now. It says an unbiased die is tossed. Unbiased simply meaning making reference to the fact that it was not tampered with. Right? Sometimes you'll see the language as fair, which means that again it does not tamper with. It's just a regular factory dice. All balanced, so it is well balanced on all sides, which meaning that any outcome has a likely chance of occurring has equal number of chances as the next, right? So we're going to look at how we're going to calculate these probabilities. Let's use a different code. So the probability of getting a 2 How many twos are on a die? How many possible outcomes are on 6? So it's going to be 1 over 6. Because if we go back to the previously mentioned information, so the probability of event A in our case is the probability of getting a 2. So it is the number of outcomes of 2, which is just 1, divided by the total number of possible outcomes. The total number of possible outcomes is the total sample space, which in our case is 6. All right. Let's maximize on the space. So doing part B here, probability of an even number. Even number simply making reference to those numbers that are divisible by 2. Thank you. So if a number can be divided by 2, that's an even number. Evenly divided by 2, that is. Alright, so what numbers are we thinking of? What are those numbers? 2, 4, and 6. So there are 3 numbers that can divide by 2, which are even numbers. What's the total sample space? 6. So if we reduce this fraction, what do we end up? Not 1.5, but a half, or 1/2. Yeah. Yeah. Right. So the probability of getting an odd number, when we say odd number, what type of numbers are we making reference to? If an even number is a number that is divisible by 2, what can we say about an odd? Yeah, but instead of what the numbers are, we first need to know what are odd numbers. Thank you. So odd numbers are numbers that are not evenly divisible by 2. So if we divide them by 2, we're going to get a remainder. So what numbers are we thinking of under that? 1, 3, and 5. Thank you. So if we say 1, 3, and 5, that means we have 3 numbers out of the 6, which gives us the same answer as even number, which is a half. Part D, a prime number. What do we know about prime numbers? All right, so when we say prime number has only 2 factors, 1 and itself, don't it? So a prime number can only be divided by 1 itself. A prime number is only divisible by 1 and itself. A prime number only has 2 factors, 1 and itself. We are saying itself because it is making reference to whatever that prime number is. So 1 can go into the number and the number can go be divided by itself, right? What numbers are we thinking of if we are talking about prime numbers? So it is hmm? What is your first prime number? Huh? 2, 3, 5. So 2 is the only prime number that is both um, even and no, even and prime. Yeah? So, because normally prime numbers are divisible by 1 itself, but 2 is a number that is an even number. So it is also an even number and a prime number because a prime number must be divisible by 1 and itself, which would account for the number 2. All right. So what do we end up with? So it is going to be 2, 3, and 5. So we end up with 3 over 6, which is equal to a half. Right? And the last one says a number that is a multiple of 3. When we say a multiple of 3, what are we making reference to? All right, so multiple of 3 simply meaning 3 can be divided into this number without me. Or if you multiply 3 by a number, you get that number. Right? So 3 is a factor of that number as well. So those are ways you can think about it. Go again? All right, so it will be 3 and 6. So how many numbers are there? How many numbers? 2. So it's going to be 2 out of the 6, which works out to be 1/3. Right. Variable. Yeah. All right, so right here, we're going to be looking at an addition to what we looked at in the, so for, if you notice, two of the examples here point to or and one point to not. Where, in a few examples to come, we're going to be and, all right? So let me just point out what you should know when you're looking at these events.
Number one, the graphic book is
Yeah, events.
thank
Yeah. All right, wait a second. I should point out to you that there are two formulas for this. There is probability of A or B. So I'm in space, so let me scoot over it. All right, so Mutually exclusive event, meaning that the two events cannot occur at the same time. Notice the condition of or. If I say to you, you can have the tablet or the phone, there's no way to have both of them. So it's one or the other. So or meaning that it cannot be both at the same time. So we're going to look at what is happening in this question and see if we can answer it based on some of the things that we have now been exposed to. It says in a tube of sweets contain 10 red, 7 blue, 8 green, and 5 orange. If a sweet is taken at random from the tube, what is the probability that it is red? Firstly, we need to know what is the total sample space. What's the total number of sweets? So you have 10, 7, 8, 5. What we end up with for our total? Huh? 30. So the probability of getting a red sweet, how many reds is there? What's the total? 30. So if we reduce this, always write your probability in their simplest form, either as a fraction or a decimal. So we're going to get 1/3. Go again? Yeah, man. Yeah. Orange. How many orange sweets is there? So the probability of getting an orange sweet is going to be equal to 5 out of. So we get 1/6. Thank you. All right. Part C, the probability that it is red, green or red. So the probability that it is green or red is going to be equal to the probability of green plus the probability of getting red. How many greens is there? 8. And how many red is there? 10. So it's going to be probability of green is going to be 8 out of 30. Probability of red is going to be 10 out of 30. Because their denominator is the same, you can just go ahead and add the numerators. So it's just going to be 18 out of 30. And then we can reduce 16 to 18. 16 to 18. 16 to 30. So we can reduce it to 3/5 in its simplest form. Right? And then the last one is the probability that it is not blue. So the probability that it is not blue is equal to 1 minus the probability that it is blue. So it's going to be 1 minus. How many blues is there? We have 7 blue. So it's going to be 7 over 30. So 1 is the same thing as saying 30 over 30. Or 1 with a D. How can we write 1 with a denominator of 30 is 30 over 30. Because 30 divided by 30 is just 1. Minus 7 over 30. So we can keep their denominators the same. If the denominator is the same, we can just subtract the numerators. 30 minus 7, 23 over 30. And this would be our answer in the simplest one. Look and let me know if there is anything I need to clarify. Go again. All right, so we're dealing with card packs. Maybe for many of us, we would have played with cards before, so we understand how the deck is set up. Just in case we're a little bit unsure, I'll point it out for us. So we have a total of 52 cards. So we have what are called face cards, and those are king, queen, and the jack. and there is four of each. You have ace, there is just four cards. You have your number cards, and that starts from 2 and goes all to 10, and there's four of each. And then you have them in terms of colors. You have black cards, huh? Remember, it's the ace. When in terms of game, sometimes they use the ace as a one. So yeah, black cards, um, and those are the spades and the clubs. And it's 13 of each. And then you have the red cards, which are going to be hearts and the diamonds. And then there is 13 of each. So that is how your deck is set up. All right. So what is the probability of getting a 7? So the probability of a 7, how many sevens are there? 4. There's gonna be 4 out of 52. What is this in its simplest form? Thank you. 1 over 13. Thank you. Part B. What is the probability of getting a heart? What's the probability of getting a heart? How many hearts are in the pack? See there? Okay. So it's going to be 13 out of. What is this in its simplest form? 1 over 4 quarter. So we want the probability of getting a 6 or a red card. Pay attention to the language. So it is the probability that we get a 6 or a red card. Now, we're going to use this formula says the probability that it is a 6 plus the probability that it is a red card minus the probability of the card that is 6 and red. Please note, there's a 6 of hearts, there's a 6 of diamonds, right? Do you agree with that? Oh, yeah. So there is a 6 of hearts and a 6 of diamonds. So why is it that we have to minus that section of it? Because the condition that we're looking for is that it must be 6 or red, not 6 and red, or meaning that it must be one or the other. It cannot be both. So it can be a 6 or it can be red, but it cannot be both 6 and red. So you have the 6 of hearts and you have the 6 of diamonds. Can't use those. Those have to be out. Because those two cards are both at the same time 6 and they are red. Alright? So how many 6 are in the pack? So it's going to be 4 out of 52. How many red cards are in the pack? 26. So it's going to be 26 out of 52. How many cards did we say are 6 and red? Yes. We just mentioned them. They are 6 and red at the same time. 2. So you have the 6 of hearts and the 6 of diamonds. Those two cards are both 6 and red at the same time. So since their denominators are the same, we can just simplify them accordingly. 4 plus 26, that's going to give us 30 over 52 minus 2 over 52. And this is going to be 30 minus 2, which is going to give us 28 over 52. What is this as a fraction in its simplest form? Seven over 30, right? 28 divided by 4 is 7, and 52 divided by 4 is 30. Alright, is there any part of it so far that is not clear to us? Need what? Alright, let's get a look back here so we can pay attention to something. For probability, we need to calculate the probability of an event. Give an interpretation if the probability of an event occurring is 1. Calculate the probability of an event occurring using statistical diagram. That we're going to be looking at. This one says express the probability of an event occurring as a percentage. Now, all of what we have done so far, we can express them as a percentage. But what we're going to do is that we're going to look at another question, and what we're going to do for those questions, for those answers, we're going to represent all of them as percentages. So after we get the answer, we're going to represent them as a percentage. So we're going to go through another question. All right, let's look at one of the diagrams that we used earlier. Let's look at a question for one of the diagrams. Well, one of the sample space that we used earlier. So earlier we represented the sample space of this, and what I'm going to do for ease of remembering, I'm just going to represent it again. All right, so this would be the sample space, the total. That would. So let's go ahead and see if we can come up with a solution. Let's write it here. What would be the probability of getting two heads? Yeah. How many outcomes would give us two heads? Huh? One out of how many? One out of four. Thank you. Part B, what is the probability of getting two tails? One out of four, which is this outcome here. All right. I did remember, I did mention I'm going to represent them as a percentage. So let's go. So if I'm going to represent this, so this is it as a fraction. If I'm going to represent it as a decimal, so it will be 1 divided by 4, which is going to give us 0.25. So this is it as a decimal. And if I want to write it as a percentage, all I would have to do is either multiply percentages out of how much again? When you're calculating percentage, it's always out of 100, right? So all I would have to do is multiply the quarters by 100 or the 0.25 by 100. So go ahead and tell me what is 0.25 times 100. Yeah. So it's going to be 0.25 times 100 equal to, so we'll get 25%. So that would be the probability as a percentage. All right, same thing here. This is the answer as a fraction. And if we say 0.25 times 100 is going to be equal to 25%. Right? So that's how we'll go ahead and present it as a fraction. It is the same, but you have to look at it in terms of which die is it on. So you have two of them. So sorry, coin. Which coin is it on? Is it a coin one or is it on coin two? Because remember, each coin has two outcomes. So that's why the experiment is paying attention to what is happening each coin. Right? So the probability of getting a head and a tail would be 2 out of 4, which is just as a fraction, as a simpler fraction, it would be, thank you, a half. So a half times 100, or if you want to write 0.5 times 100, either of the options would give you 50%, right? So there is a 50% chance of getting a head and tail. All right, let us continue. One of the things that we're going to be looking at now is what we call probability tree diagram. Yeah. All right, so we're going to represent the information that we have here on what we call a probability tree diagram. It says a bag contains 4 red balls and 3 green. A ball is taken at random, then put back. Putting back is important because if you put back the ball, you have changed the sample space. A second ball is then taken from the back. What is the probability that both balls are the same color? At least one ball is green and the balls are of different color. Right? So we're going to look at and how it looks on a tree diagram. So it may sound like we're going to be drawing like a tree that we see on the outside, but no, it is just the description of it because it has what we could consider to be links. All right, think about it this way. Here's my bag, and in this bag I have the different balls. I have 4 red and 3 green. Right? I'm going to pick 2 times. So I'm going to have my first pick, and then I'm going to have second. Maybe I don't want it to be so far apart because some space in. So I'm gonna put my first pick right here. Okay, second. So let me get this. Let's see if we can follow and agree with the information. On your first pick, is it possible to pick a red ball? Yes, sir. Is it possible to pick a green? All right. So I'm saying the probability of getting a red on my first pick, what would be that probability? 4 out of? 4 out of? 7. 7. What's the probability of getting a green? 3 out of? How many is in the bag? 7. So it's 3 out of 7. If I pick the first one and it is red, and I put it back into the bag, how many balls are in the bag? 7. Why? Because I put it back. On my second pick, is it possible to get a red on my second pick? What would that probability be? 4 out of 7. On the second pick, is it possible to pick a green? What would be the probability? No man, second pick, we're still talking about 3 out of 7. Let's go. Let's understand the context. I'm going to pick the very first time. There is somebody with a bag and they come and say, pick a ball. So if I go in the bag and pick a ball and my first ball is red, I have 2 picks and that first ball is red. And notice, I write it down, I put it back in the bag. On my second pick, what are the possibilities on the second pick? Is it possible on the second pick to pick a red? Is it also possible that the second time around you could pick a green? So what we're saying is that your first pick could be a red and the second pick a red, or your first pick is a red and the second pick is a green. When you pick a green on the first outcome, is it possible that you could also get a green on the second outcome? What would that probability be? 3 out of 7. Is it also possible that on the second pick it could have been a red? What would that probability be? 4 out of 7. Because I can pick the first green and then I pick another green. Or I can pick the first green and then the next one is a red. Alright? What I normally say to students once they get the tree diagram is to work out what is happening for the combination for each of the limbs. So don't wait to work it out, just go ahead and work it out right away. What do I mean? Let's look at what happens if we get a red and a red. So this is going to be equal to 4 over 7 times 4 over 7. So it's going to be equal to 16 over 49. That is getting a red and a red. The probability of getting a red and a green is going to be 4 over 7 times 3 over 7, which is going to be 12 out of 49. The probability of getting a green and then another green is going to be 3 out of 7 times 3 out of 7, which is going to be 9 out of 49. And the probability of getting a green and then a red is going to be 12 out of 49. This is important because once they ask you any information relating to this diagram, you can just use the information over here without going back to do any calculation, right? So you don't have to go back to do any other calculation. Let's look at what they ask us. What is the probability that both balls are the same color? So what are we saying? It is the probability that it is red and red or green and green. Alright? So it is the probability right? So we have that already. So it is the probability of red and red or probability of green and green. But we already did work it out. What did we do? So for red and red, it's 16 over 49. So it's going to give us 16 over 49 plus green and green is 9 over 49. So it's going to give us 9 over 49. So this is going this is going to be 25 over 40. And that's it. Alright, because we would have already gone ahead and done the calculation on the limits. Alright? So the calculation was done on the limits. So red and red is 16 over 49 and green is 9 over 49. So when you add both combinations together, you do 25 over 49. Anything I need to clarify before we continue? All right, let's look at the next one. At least one of the balls is green. So at least one is green. So this is equal to the probability of red and green or the probability of it being green and red, or probability of it green and green. Because it says at least one of them is red. Look at this combination. At least one of them is green. Is there a green here? At least one. Is there a green here? At least one. Is there a green here? At least one. Only that there is two, but it says at least. So the least amount it can have is one. Huh? Yeah, man. So even though there are two greens, one of them is a green, so it's at least one of them is green. The only combination that wouldn't work is where they are both red. So what I mean? So we're going to use these three answers here. So it's going to be equal to 12 over 49 plus 9 over 49 plus 12 49. Right? So that is what we get. So we end up with 33 over 49 for our answer. So that would be the possibility of at least one of them is brief. And as I mentioned to you, once you work out the outcomes on each of the limbs, yes, then it's easier to just get the information from the limbs and just go ahead and check. And they're being verified right now. So very start. Okay. They will unsubmit them, so I cannot. Because this week was not done up. So they are unsubmit. Sorry. Guys, all right, so the balls are different color, which means that one is red and one is green. All right. So the balls are different color. So let's look at the combination for different color. So it could be the probability that one is red and one is green, or probability that one is green and the other is red. So this is going to be 12 over 49 plus 12 over 49. So that's going to give us a final answer of 24 over 49. Let's look at another example. So this is the next one. Okay. All right, so you need that you would have got some time to write it off and you start working the question. Let's go ahead and look at it. 3 red, 2 green, 4 yellow. How many balls we have in total? 9. So here's our bag. So we're going to have first pick, then you have the second. Can your first pick be a red? What's that outcome? 3 out of 9 is the same thing as? Well, let's keep the denominators the same for here. On your second pick, would you pick a red? What would that outcome be? Pay attention to this context right here. 2 out of 8. On the second pick, when you pick a red the first time, is it possible to pick a green? What would that outcome be? 2 out of 8. Is it possible that you could have picked a yellow? What would that outcome be? 4 out of 8. Alright. Yes, because it's 3 balls. On your first pick, would it be possible that you could pick a green? What would that be? 2 out of 9. Is it possible that you could have picked another green? What would that be? 1 out of 8. Is it possible that you could have picked a red? What would that be? 3 out of 8. Is it possible that you could have picked a yellow? What would that be? 4 out of 8. Alright. On your first pick, is it possible that you could have picked a yellow? What would that be? 4 out of 4 out of 9. Is it possible that on your second pick it could have been a yellow as well? What would that outcome be? 3 of 8. Is it possible that it could have been red? What would that be? Is it possible that it could have been a yellow? Sorry, green, as we did yellow already. What would it be? 2 out of 8. So these are all your possible outcomes. What you now need to do is to work out what would be the result for each. So for both of them being red, it's going to be 3 out of 9 times 2 out of 8. And we know that these are fractions that we could have easily well reduced. Alright? But what we want to do, yes, but the thing is, all of them will not be reduced evenly, right? So some can reduce while some will not be able to. So the best thing you can do to make sure that you can use your calculation as simple a form as is possible, keep the denominators the same. So you can say 3 times 2, which is going to give 6, and 9 times 8 is going to give us 1. Nothing wrong with that. For this one, it's going to be 3 nines times 2 eights, 6 out of 72. For this one, it's going to be 3 nines times 4 eights. For this one, it's going to be 2 nines times 1 out of 1 eighth. So see what I mean by keeping the denominators the same? Yeah, you can simplify afterwards when you're doing the actual calculation. So 2 nines times 3 eighths. So this is going to be 6 out of 72. For this one, it's going to be 2 nines. See, 2 nines times 4 out of 4 eighths is going to be 8 out of 72. Then this is going to be 4 nines times 3 eighths. So this is going to be 12 out of 72. So this one is going to be 4 nines times 3 eighths, which is going to be 12 out of 72. This one is going to be 4 nines times 2 eighths, which is going to be 8 out of 72. So all you would have to do now is when you're answering the question, look which calculation applies to which, and then you just use it accordingly. Take for instance, it says here that both balls are the same color. So they are either both red, both green, or both yellow. Let's look at both red. Both red would apply to this one. If they are both green, it would apply to this one. And if they are both yellow, sorry. And if they are both yellow, it's this one. So those are the 3 fractions that we would use for them being the same color. So the probability that they are same color is equal to the probability of it red and red or the probability of it being green and green, or the probability of it being yellow and yellow. So it is going to be 672. So it's 672, 272. Was it 2? And 1272. So what is this going to give us? It's going to give us 2072. We can reduce it and simplify it down. So remember, it's always written as a fraction in its simplest form. So 20 divided by 72, what would we get? Five over. What do you get? What do you get when you divide it? 10. 5 over. Alright, that's part A. Part B. What did part B says? No yellow ball is taken out. So let's look at the probability of no yellow. Right? So we're going to look at all the fractions that apply. Oh, I could have just kept those in. So no yellow is going to be equal to 1 minus the probability of getting at least one yellow. Right? So it's going to be equal to 1 minus. We want to get at least one yellow. So this combination is yellow. This combination is yellow. And this combination is yellow. So if we add up these three and subtract it from 1, we'll get the probability that there is no yellow. Right? So 12 and 8. So it's going to be 1272, 872 plus 1272. So this is going to be equal to 1 minus 32 over 72, which is equal to, it's the same thing I'm saying, 72 over 72 minus 32 over 72, which is going to be 40 over 72. Okay? 40 divided by 72, what in somebody. Okay. But 10 out of 18 can be reduced. That's going to give us 5 out of 9. Okay? Yeah, man. If you write it as a decimal, that's also fine. If you write it as a percentage, that's also fine. Huh? No, man. So the answer as it is, you can either choose to represent it one of three ways, either as a fraction, a decimal, or a percentage. Either way you choose, that's complete. And then, well, it depends on what the question asks you, but if it's just on a normal, you can just represent it as a fraction. And then at least one yellow ball is taken out. So we know the combination for that already. Because see, we find it here, probability of getting a yellow. So probability at least one yellow. It's going to be equal to 12 of 72 plus 8 of 72 is 12 of 2, which is going to 32 72. 32 divided by 72, what you end up. Huh? We get 4 minutes. Huh? Come on, them one that can represent all the fractions as surds. So these are some of the questions that you could get when you're talking about probability, right? So it's just for us now to bear these things in mind. When we start doing statistics aspect of it, when we're looking at frequency table, we're going to also learn how to calculate from a statistical diagram, which is like a scale, right? So we're gonna stop here with it for today. All right.